video, we are going to talk about the ceramic scaffold. What is ceramic scaffold?
The introduction of ceramic scaffolds. Porous templates, referred to as scaffold, are thought to be required for three-dimensional tissue growth. Bioceramic, a set of fully, partially or non-crystalline ceramic, for example, calcium phosphate, bioactive glasses, and glass ceramic, that are designed for the repair and reconstruction of diseased parts of the body, have high potential as scaffold materials. Traditionally, bioceramic has been used to fill and restore bone and dental defects to repair hard tissue. More recently, this category of biomaterials has also revealed promising applications in the field of soft tissue engineering. A key component of this strategy is a synthetic framework referred to as scaffold, which serves as a guiding to a three-dimensional structure for both hard and soft tissue development, both in vitro and in vivo. Due to its open system of interconnected pores, the scaffold provides a mechanically stable environment that can host the required cell and biological components seeded in the laboratory prior to implementation, allow cell migrations, adhesion and growth, and support the organization of the growing tissue when implemented in vivo.
How the ceramic scaffolds is produced. Highly porous ceramic scaffolds have been fabricated from a 70% of silicon dioxide and 30% of calcium oxide. Glass powder, which is 150 grams, was mixed with 250 ml distilled water and 2 to 3 drops of Dolapit CE64 added before processing in an extrusion mill using zirconium dioxide milling media. At the end of the milling process, the slurry was separated from the milling media and freeze-dried. The freeze-dried powder had a mean particle size of 3.2 micrometer measured by light scattering. The scaffolds we use a modification of the lost mold process for ceramic manufacture combined with gel casting using stereolithography. After sintering at 1200 degrees Celsius, the gas crystallized to a structure of wollastonite and pseudo-wollastonite grains in a glassy matrix with a bulk porosity of 1.3%. All scaffolds had a simple cubic structure with an internal porosity of approximately 42% and internal pore dimensions in the range 300 to 600 micrometer. These 3D scaffolds will be referred as 300 scarf, 400 scarf, and 600 scarf respectively. Method of preparation of scaffolds. First, fiber bonding. Second, emulsion freeze drying. Third, solvent casting. Fourth, high pressure processing. 5. Gas foaming. 6. Thermally induced phase separation. 7. Electrospinning. 8. Rapid prototyping.
Bone replacements are frequently needed due to trauma, bone neoplasia, stabilizations of spinal segments, and more generally in many orthopedic, maxillofacial, and craniofacial surgeries. Many injuries are not adequately treated because bone defects above a critical size cannot be repaired through the natural growth of bone tissue. For the repair and regeneration of bone defects, tissue engineering strives to produce 3D construct that can support mechanical load and provide a template in which cells can migrate and colonize. The optimum attribute of a 3D scaffolds are summarized as follows. 1. The biomaterials should not only be biocompatible but must also support cell adhesions and proliferations. The material should be at minimum osteoconductive but ideally osteoinductive. The biomaterials should resorb over time, and the resorption rate of the implant should match as closely as possible to the regrowth of the new tissue. For these reasons, artificial graft or scaffolds are interesting and challenging candidates for stimulating bone regeneration and for supporting the newly formed bone. Three-dimensional scaffolds should show a highly porous, open structures to allow a proper vascularization of the implant, as well as the flow of nutrients and waste products through the scaffold.
As we know, ceramic scaffold has an advantage and disadvantage. The advantage is ceramic scaffold are high hardness, which is its resistance against burnishing from third body wear. Next, ceramic scaffold also has good wearability and has high compressive strength. And lastly, ceramic scaffold is inert wear debris, which is no adverse effect. While for disadvantage, ceramic scaffold has high brittleness, which is it has unexpected fractures and thicker component. Besides that, ceramic scaffold also has a limitation in component fixation. And next, the disadvantage for ceramic scaffold is it has high elastic modulus that cause stress shielding effect and bond loss. Lastly, ceramic scaffold do not have bioactivity that can cause soft tissue interlayer.